live. Is that what I'm supposed to press?
Well, I mean, I assume so.
Oh, lol, I didn't even realize I was supposed to click go live.
Are we live now?
Oh, okay, I think we're live now. Well, I hope we're live now. Let me refresh
Yeah,
this.
yeah, it's working.
Okay, it's working. Nice. Cool. Well,
Oh, Max with stuff. Nice.
okay.
Am I supposed to like edit the overlay like IRL?
No, we do that at the end, right?
Yeah, sure.
Alright, do you have the paper?
Oh,
Doesn't matter.
I gotta do like the thing where
I'll just screenshot, yeah, and paste it into here.
yeah, okay.
There we go.
And how do you delete this?
Also, I even have transitions in my streaming thing where I can transition between these problems. Oh, so good.
Wow. Are you,
If you're not watching the stream, yeah.
yeah.
Okay. Yeah. Oh, look at that. We deleted it.
God damn.
Okay, so yeah, should we just get started?
Sure.
Yeah, and you're gonna get your food coming soon, I guess. So
Yeah, food is
yeah,
coming soon.
Ishan is gonna take a break for a while and eat some food. You're like
Uh,
self quarantining, right?
yeah, yeah, big time.
Sad. Yeah. Oh well. Got to do some maths to get the spirits up. Clearly.
Of course. So sad.
Yeah.
Anyway, this problem.
Okay.
I mean, you could just write out the algebra, right?
Yeah. So
Go on, Tony, write it out.
n equals x plus k. N equals a squared minus k.
Wow.
Find all k such there are infinitely many k numbers. Okay, interesting.
Right. Well, if k is even, right, you just add k over 2 squared. Then you get like two squares which differ by a small amount.
Doesn't that differ by 1? Wait, what? K? Oh, k over 2 squared. Right, say that again?
If you like, just like a squared minus. You write it down. Like you have like a squared minus k equals k squared plus kx, right? And you just add like k over 2 squared to both sides.
Right. Like this.
Yeah.
And then,
Then what is it? You have two squares which differ by some fixed amount, which is sad.
right.
This is x squared.
Oh, yeah, no, yeah, sorry. Um, all right, well, let's do some small cases then, I guess.
I mean, k equals 1, that seems
Yeah.
more.
Okay, it's a one number. Wait, surely there are like, oh wait, hang on. I don't think there are there are practically no one numbers, right? Like 1 times 0 is the only one number.
What is it? It's a
Right?
one less than
There's one
something
less
and
than
something
one.
something. Yeah.
But for all the other numbers, you need like,
Food has arrived.
all right,
Second.
nice. So Ishan's now gone to get food. So yeah, for the one numbers, right, you have like a squared minus 1. And you want this to be equal to x squared plus x. Except that like this side is going to be a minus 1, a plus 1, which is slightly problematic. So yeah, here you can just use like, what is it called? But basically like if x is one number and then a is like the next number, the left side is still like way bigger than the right side. So here you have just like, yeah, essentially, oops. You have a is bigger than x, of course, but this implies that a squared minus 1 is bigger than x squared plus x. Unless a equals like 1 and x equals 0, in which case it does work. But that's like only a single one number. So one numbers are basically like, there are no one numbers except for 0.
I've got my food.
Nice. What is it?
We're eating today. We can have chicken, beans, potatoes. I don't know, whatever British people eat.
Oh, nice, nice. Wait, what food is it? Is it like your college food and your college delivers it to you?
Yeah.
Oh, nice. Okay. I thought it was like you ordered it from outside, but yeah.
I don't know.
Are there any two numbers?
But there can't be any two numbers.
Why not?
You get a squared minus 1 equals a plus 1 squared.
Isn't it a squared
X plus 1
minus
squared.
2?
Yeah, you just add 1. You get a squared minus 1 is x plus 1 squared.
Wait, what? Say that again? What?
Hey.
I'll write it down.
So if k equals 2,
Yeah.
you get a squared minus 1
Okay.
equals k plus 1 squared. I mean, x plus 1 squared. And clearly there's only finitely many solutions.
Oh, right. Yeah. So this practically has no solutions as well.
For any k even, you can do that.
Right. Oh, because this equals k. Yeah, no, sorry. I like just figured out what you were trying to do here.
Nice.
Yeah. Okay. But what if okay, right, yeah. Fair enough.
And there's so much sauce.
Nice. Is it good?
It's pretty food.
It's British food.
I mean, I've lost my taste, so.
That's true as well. Has it actually affected you much?
I had a fever, and then back to normal, back to math.
Nice. Always back to maths. All right, 3 numbers. Are there any 3 numbers? We have a squared minus 3 equals x times x plus 3. Surely, okay, hang on. Surely the way you want to do this is like, just, so a squared equals x squared plus kx plus k, right? And then you try to factorize this side as much as you can by difference, by completing the square. So you just get like x plus k over 2 squared. And then the difference is, you want a plus k minus k squared over 4. So you need k minus k squared over 4.
To be the difference of 2, like half in, like.
Yeah, to be the difference of 2 squares.
Like multiply everything by 4.
Yeah, let's do that. Okay. So then we get 2a squared equals 2x plus k squared plus 4k, minus k squared. And this is separate from that.
Okay.
Right. Let's go to the next page.
We should be done in 4 pages, right?
Sorry, what?
So we should be done in 4 pages, right?
Oh yeah, clearly. You mean, one page per problem. Easy. Yeah, if you just write really tiny, you can do everything in one page. Okay. Yes. So 4k minus k minus 2 squared. But for any particular k, this is a finite expression, right? And like it cannot be the difference of infinitely many pairs of squares.
K equals 4.
What? Oh, right. Of course. Yes, but for any other k, there's no solutions, right? So k can only be 4.
Yep.
So yeah, essentially, the solution to this problem is, for the viewers, is basically that you have some square number equals some other square number plus the difference of 2 squares. And if you just fix this number here, the difference of 2 squares, then there's only finitely many solutions for a squared and b squared. Just because the way that squares work is like, they grow quadratically, right? So they, at some point, the difference between 2 consecutive squares is going to get larger than c. And at that point, anything higher, any higher squares are not going to differ by, they're going to differ by more than c. So then you get finitely many pairs of a and b which work, which means that the only c which has infinitely many solutions is when c equals 0. So if you want infinitely many a-b pairs, so you get c equals 0, which implies that 4k minus k squared equals 0. So this has 2 solutions, right? K equals 0 or 4. But is k a positive integer? So yeah, k is a positive integer, so k equals 4. Is the only possible solution.
K equals 4 clearly works. Right.
So what's your construction? I mean, obviously it works, but...
It's like the obvious one.
So obviously you
That's
need
not very
to
helpful, is it?
explicit construction.
You just take any two integers which differ by 4 work.
Yep, that sounds good. So if you just take x multiplied by x plus 4, you get x squared plus 4x. And this turns out to be x plus 2 squared minus 4. So we have a family of solutions. Actually, you can, yeah, so basically, literally any number works, right? So like, what are we even looking for?
If it satisfies one, then it satisfies
The integer
other,
n is a product of 2. Yeah, so n equals a squared minus 4 for a in natural numbers. Looks good. Do we do the next question? And look at this transition, guys. Oh, such transition.
Good.
Sorry, Ishan, you can't see that because you're in... unless you're watching the stream. But yeah, I'll also take a screenshot of the next one.
Oh, okay, I see. I saw the transition.
Oh, nice. There's like a 30-second delay though. Alright, so that's the second problem. Okay, functional equation. It's an integer.
Integers.
Functional equation. Didn't you have a handout on this? Someone had a handout on this. It was like Rick, right?
Rick.
Yeah.
Get him in the chat.
Oh yeah. We need Rick. All right, let's do this. So okay. Interesting. What do we sub? Y equals 0. Yes.
Yes, that's great sub. Oh no, we can't sub y equals 0.
Oh, bruh. Sad. Let's sub y equals 0 anyway and see what we get. Okay.
True.
But this is illegal technically, so. I mean, there's no reason. I don't see any reason why it's restricted to positive integers right now. But
it's probably like some induction at the end.
Maybe, yeah, that could be why.
If you just sub x equals like some constant, then you get f is linear on the even numbers.
Oh yeah. That's fair. So you sub x equals some constant, you get 2y. 2ya equals b f of 2y. So this means that f of 2y equals 2a over b times y.
Tony, where did the xy go? 2xy.
Oh, that's an xy. Limao. I didn't even notice. Clearly, I missed out the first step of solving any problem, which is to read the problem 4 times.
Anyway, if you plug x equals 1, it still works.
Yeah, just plug x equals 1, I guess. I think x equals 1 is probably better. So here you get, you still get this. Okay. Can we just solve this for even positive integers?
Probably not.
What? Why not? Surely just like... So this is just cy, right? Like...
Yeah. And this implies that f of 4y is even, right?
Sorry?
This implies f of 4y is even.
How?
Because f of 2y is an integer.
Yeah. No. Because
F
if
of
you
4y is
substitute
just
y
integer.
as even, then this is also even. Yeah.
So then if you like put x even, then this term you can use a linear thing on. No, you can
Right.
put this if x is a multiple of 4, then you can use a linear thing on that.
Right, yeah. Okay, so... what do I put here? If of 4k equals even. Um... Right, so your idea is to sub x is even.
Wait, what's my idea?
It is, right? Because then you can use what we just did on like this bit.
Yeah.
So you get 2y if of 4k squared plus 2k. Now we know this thing in here is c 2k squared. So 2ck squared. And this is equal to if of 2k plus 1. Okay, so we have an odd number here, which is promising. Times 4ky. We can simplify so much of this. Okay, so now this is... sorry, you don't get that. You get c squared k squared plus 2ck, right? Oh, sorry, just ck. Equals if of 2k plus 1. And this thing becomes 2cky, I believe. Right?
Yeah.
Cool. Okay, so doesn't that just give us... That gives us a formula for both odd and even, right?
What is it? F of 2k plus 1 is what, c plus 1? What? No, ck plus 1.
Yeah. So if you rearrange stuff, f of 2k plus 1 is equal to ck plus 1.
Nice.
I think we're pretty much done here. So f of can we combine these two into a single equation? I mean, we have like f of 2x equals cx, and f of 2x plus 1 equals cx plus 1.
Yeah.
And f of 2x plus 2 is, it's cx plus c. That's why you can't condense it into a single.
I mean, if c equals 2, then it's very nice, right?
Yeah. That's the hope, right? Yeah. Okay, so we can't condense it into a single equation, but maybe we can just plug them in and solve. But it might be a bit like we might need to do different cases for odd and even, right?
Although, well, you've done the x even case, so we want to do the x odd case, right?
What do you mean the x odd case? Oh, right. So you're saying like if x equals 2k plus 1, then we can simplify. Okay, yeah, that works. Yeah, let's go to the next page. Oops, no plus 1 here. Okay, we also know that f of 2x plus 1 is cx plus 1. And no, actually that third thing is not important. So now we do x equals 2k plus 1 and plug that in and see what we get. This might be a bit bashy. So we get 4k squared plus 4k plus 1 plus 2k plus 1 equals f of 2k plus 2, f of, oh god.
No, 2xy is easy. Right, it just becomes cxy.
What, does it? Oh, right, yeah, no,
Xy
you're
is
right.
even.
Cool, so this is 2y f of whatever this is.
2c x squared plus x.
2c, you mean k squared,
Okay,
plus
squared.
2ck plus 1, right?
Yeah.
Plus 2k plus 1. And this part
Oh,
is just
even.
cx plus c. Did I make a mistake?
Let's see. That should be ck plus c.
Oh, yeah. And finally, we have 2y of, oh wait, this is even.
Yeah. You have c squared.
Yeah, c squared k squared plus c squared k plus c plus ck, right?
Yes.
All right, and now I guess we just compare terms. Yep.
Oh wait.
Well, I mean,
There's,
yeah, I'll just rewrite it like with one less c.
there's the 2 here. You can rewrite with all the C's gone, right?
Wait, can we?
Wait, no,
You can't.
never mind.
Wait, we can factor out a k plus 1, right? Because this side has a k plus... Oh, no, we can't.
Yeah.
Oh, wait, we
Yeah.
can. We can. Because it's like this. I forgot to put the brackets in.
Yeah.
So it becomes 2 of c... Wait, hang on. How do you factorize this?
CK plus 1. I think.
k plus 1, right? Oh, ck plus 1,
Yeah.
k plus 1. Yeah. ck plus 1, k plus 1 equals k plus 1 cx. And so the k plus 1 cancels out, and you just get 2 ck plus 1 equals cx.
You expand X.
Yeah. So x is just 2k plus 1. This implies, well, you get 2ck plus 2 equals 2ck plus c. Implies c equals 2. Done.
A.
Nice. And now we just need to check that the function works. So, yeah, this just implies that f of x equals x, right?
Yeah.
So this implies f of x equals x, and obviously you just need to check it works, because right now this is the only function that could possibly work. So that's just... Wait, what? What's this?
Give the answer.
So that's just 2yx squared plus 2yx on this side, and you have
8. Factor it out.
2x squared y plus 2xy, and both sides are the same, so it works.
Okay. Yeah.
Done. Nice. Third problem?
No.
Or should we just skip to the fourth problem? Yeah, clearly we should have gone 4, 3, 2, 1. That's the big brain strats.
Flex. Problem 3.
All right. Let me switch.
Hey, this is way easier than last year's BMO2.
It is, especially problem 2. Last year's BMO2 problem took me like 1.5 hours.
It took me like 3 hours.
Yeah, I know. Yeah. I heard it was really hard for a lot of people last year's.
Yeah.
Problem 2. Okay. Oh, let me get the screenshot.
So what have we had? We had a number theory and algebra. So this is either combi or trio. Oh, combi. Damn it! I always have geo problem 4. And
Alright, is this combi?
It looks like it. It has cards, so from just
Yes.
this argument here, it has
Yeah.
to be combi.
Has to be combi, yes. Hmm.
So you have boxes, and then you put the boxes in a pile.
Yeah, apparently.
This is like I'm a 2024 through.
Is it?
Not
Oh,
really, but it reminds me.
yeah, it does. It's kind of, yeah.
Something. Okay, I'll draw a box.
Right. So it's basically saying that, like, after some
Okay.
certain point, if you have enough decks of cards, then, like, there is some grouping of the boxes that make them, like, the same, right?
Yeah. Yeah. Wait, what? This wording is so bad. I'm confused.
Is it? Okay, so
Don't explain this problem to me.
so basically, like, um, you have n decks of cards, where each
Yeah.
deck has the cards 1 to 50,
Okay.
right? And you distribute them into as many boxes of cards as you like. So you have a bunch of boxes.
You choose the boxes, or you
You,
choose?
you I think you
thought
choose the
chose.
boxes, right?
What? I don't think so, right?
It just says the cards from n identical decks are put. Sorry, you don't choose the boxes. Sorry. I mean, like, as in someone
You
else
choose the
chooses the
piles, right?
boxes. You choose the piles. Yeah. So you distribute all your cards into these boxes, or, well, someone else distributes them, and you have to prove that no matter how they distribute them, if you have enough decks, right, then no matter how it's distributed, you can always split these boxes into two piles, which contain the same cards. Yeah. Does that make sense?
Oh, okay. I'm stupid. Never mind. I see. Thought it was like if the number of labels in each thing is even. I don't know why. Okay, never mind.
Okay.
Okay.
Okay, so clearly, actually, I'm not sure about this anymore. Is 50 in 2022 random? Like, can we make 50 like 1,000?
I don't think so, right? Because you have like a eventually statement, right? So
What do you mean eventually statement? Like, sure, the capital N won't be the same, but is it true that eventually it will work?
Surely.
Like, what I'm saying is, like, is there some relationship between 50 and 2022 that makes this work?
I doubt it, right?
Yeah, I doubt it. I doubt it. Yeah. Although it is very suspicious that it's labeled 1 to 50 instead of like 52 or 54.
Yeah. Actually, you
It's
only
not.
need to find one subset, right?
You mean like one subset containing half of them, right?
But
What do you mean?
the piles don't have to be equal, right?
The piles. No. The boxes. Wait, no. The piles have to have equal numbers of cards,
Do they?
don't they? Because that's what regular means, right? Regular means that
Oh, like the two piles, they can be like any different number.
they can have any different number of boxes, but they have to have the same number of cards and the same like amount
What?
of each card, don't they?
Are you sure?
Because a pile of boxes, so let's say this is pile A and this is pile B, is regular
Yeah.
if that pile contains equal numbers of cards with each label. So like if there's a card numbered 1 in A, there has to be a card numbered 1 in B. If there's two cards 1 in A, there's two cards 1 in B.
You sure?
Wait, how are you interpreting
I thought,
this?
bruh. Okay, I thought it was like A, like you have each of the numbers 1 to 50.
Yeah.
Like k times with some k. Each of them are k coterms, and in B they have 1 to 50, like n minus k times.
Oh. Oh.
Think.
Oh, right. Yeah.
Otherwise, this wouldn't work if n was odd, right? That's why I was like so confused at the start.
Yeah, no, you're right. You're right. Oh, yeah, it wouldn't even work if n is odd. Oh my god. Yeah. How to understand problems 101 with Tony and Ishan.
How long do we spend that doing that?
Um, roughly
10 minutes,
10
right?
minutes, I think.
No, that's okay. We can start solving problem.
Yes, we can finally start solving the problem. Okay. Okay, so surely this is just linear algebra, right? Surely, as in like, so you treat each box as a vector, and the one norm of each vector is at most 2022, and
Okay,
you just
yeah.
like they're just not linearly independent after a certain n.
Yeah, probably.
Or at least that's the main idea. Yeah, like as in.
What are you taking like the z z to 50 like mod out? Z.
Wait, what?
You treat them elements in like z to the 50, right?
Yes. Yeah. So your elements are in z to the 50. So you have, or I guess they're boxes. So bk is in.
Don't you have to like mod out by
Yes. You have to mod out by like 50. Oh wait, no.
wait, okay, hold
Oh
on.
no, you don't mod out by stuff. It's like it's not in z to the 50. It's like z to the 50 with constraints.
Bro, sad. I damn. That's the 5.
But yeah, it's like yeah. So for those viewers that don't understand vector spaces or what we were just talking about, basically what our idea is right now is you take each box and you represent the number of cards of each number by drawing a column vector where the first entry is the number of cards of 1 and the second entry is the number of cards 2. And so, for example, if you have like 2, 3, 0, 1, blah, 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 that means you have 2 cards that have 1 on them, you have 3 cards that have 2 on them, you have 0 cards with 3 on them, and so on. And the constraints for these vectors is that they all have to have 50 entries, and they're all positive integers, so they're all non-negative integers, and the sum of all of the entries is less than 2022. And then maybe we can use some linear algebra. I mean, obviously, you're not expected to use linear algebra, but we're fairly sure it works, at least.
Are we? Okay, let's see.
I mean, I am. I don't know about you.
Yeah, let's go. Oh, there's only finitely many types of boxes, right?
Yeah. I mean, at most, it's like
2021 to the 50.
yeah. Shouldn't it be like 2023 to the 50?
What?
Because you can have
yeah.
all the numbers from 0 to 2022. Yeah. Okay. The main difficulty is that, like, if you consider just having one box repeated over and over, then it's impossible, right? But obviously, the cards that you don't use have to end up being used somewhere else. So
Yeah,
we just need to like quantify.
what is it?
How about this? Is it possible to show that the total number... Oh, wait, no. Maybe that doesn't help, though. Or maybe it does.
Like, induct on dimension, like...
Oh, induct on dimension could work too, yeah.
I'm thinking about it for the 2D case. That's
Yeah.
pretty not bad.
Is it?
I hope not. There's like some GCD things that are like annoying. Maybe you can do like what is it? Like like van der Waals theorem.
Lol. Yes, but
replicate like the proof.
I don't actually know the proof for van der Waals theorem.
Nice. He just like induct, induct.
Oh yeah, I know that part of it.
Do you even do the 2Ks?
Yeah, how do you do the 2Ks? Good question.
I go from like here to here without touching the center line. It's like the grasshopper problem.
Yeah, I know, yeah. Lamau. So, yeah, I guess if you like treat this as you like add up all the vectors as a series, right? Then you take some path from the bottom to the top.
Yeah.
And you have to prove that like maybe you can rearrange these vectors in some way so that you reach some point on this line which is not, yeah.
If you just like the differences, right, you get all of them must be on different diagonals. It's not very useful.
I was thinking like if you just take all the different subsets and you show that like two of them add up to the same thing, maybe that helps. But
Oh, true. Yeah.
but does it though?
Right.
Like even if you do get two subsets which add up to the same thing, how do you use that?
Yeah, good question.
It means you can get two uh, mutually exclusive subsets which add up to the same thing, but that still doesn't help that much. What if instead of adding up to the same thing, you want them to add up to like kind of like the opposite of each other, right? So then when you can put them together.
Let's see if like a lot of pigeons.
So yeah, like if you have AB, then you need to make sure that you don't get BA. Because if you can get two mutually exclusive subsets which add up to these two, then you just add them together and now you just get A plus B, A plus B.
Oh, but that sort of doesn't help. I mean, like, doesn't work, right?
Why not?
Because like, you don't get a contradiction if like you have A, B, like infinite times. Just said.
No, but as in like the way you would establish that that like these two sets exist is by counting the total. Oh wait, no, yeah, wait, no, that doesn't work. Yeah, I see what you mean.
If you can like bound the number of things that add up to a certain thing. This seems too complicated. if 2 to the n subsets, okay. Oh.
It's time to try more small cases.
Sure, like the 50-dimensional case will follow from the 2D case, right?
Yeah, I'm pretty sure, yeah. So, let's just try some stuff. Hmm.
This is so annoying.
Maybe we can induct on the number of cards as well, because, like, if you just assume that each box can only contain like at most, like, 3 cards, then it's also pretty straightforward, I think.
Is it? I feel like the cards is like the just there to keep like the
Just to keep
what
it
is it?
finite.
Just keep like the size of the vectors finite.
Yeah, exactly. Yeah, as in
Bounded.
like if it's not bounded, then you can be like, oh, what if you put all the cards in a single But,
Yeah.
but like yeah, if you reduce 2022 to like 3, I'm pretty sure it's like fairly straightforward, right? Because that means that like, I mean, you can only have 9 different vectors. If you just have
Wait, can you?
yeah, because it's like 0, 0, 0, 1. Sorry, it's 16.
Yeah, come on, mate.
Rip. There's only 16 different vectors.
But how do you induct?
Yeah, I don't know. But like, maybe you don't need to induct, right? Surely, if we can figure out how to do it for 16, or if, like how to do it when there's at most 3 cards, then we can figure out how to do it for at most 2022 cards.
For 3 cards, you like bash it out, right? It does seem like you do that for 2022 cards.
Well, can you bash it out?
Pretty sure if you give me like an hour.
Well, okay, sure, but like, is there like a nice way to do it?
Good question.
Surely, maybe what you want to do is you make a grid, right? A 4x4
Yeah.
grid, And in each square, you put the number of vectors that are in that square. So here's 0, 1, 2, 3, 0, 1, 2, 3. This is the number of A, and this is the number of B, where the vectors are A, B. Okay, so now if we have this configuration, then it's like we have 2 of 1, 2.
Or Tony, this AB plus BA argument doesn't even work, right?
Why not?
Because like if you have the same vector in both of these, then something bad happens.
No, no. But you just if they're the same one, then you just take them out.
If you
Oh,
take it out,
wait.
then it's not.
Then it's not. Okay, yeah, that doesn't work.
Sad.
That is sad.
Stupid.
Bruh, is this like last year's problem 2? Is this like the combi problem that like killed everyone?
That's his problem too. Surely not.
This is quite sad. Okay, well, if we do this grid thing, right, then it's like you can make the numbers in the grid add up to whatever you want. But someone else can distribute the numbers in the grid. And they are also subject to the condition that like the total amount of A's is equal to the total amount of B's. And you just have to find like a...
Funny, how much do you know about modules?
Sorry?
Is module theory helpful here?
I don't think so. Well, maybe you can use modules. For our viewers who don't know, a module is a vector space over a ring, where a ring is a field with less structure. So it's not as nice. And fun times.
Wait, if you just like take the 2D thing, project it on this line, right?
Which line?
This line. Like, come to the next slide.
Yeah.
This one.
Yeah.
Project it here.
Yeah.
And so all the points come here.
Okay.
You have like some collection of points that are like bounded distance away. And
Oh, right.
they add to 0. So some of them add to 0. Something. I think that's like module theory, right?
Isn't that literally just like you look at instead of looking at the vectors a, b, you just look at a minus b, right? And then
Maybe.
it's yeah, actually it's pretty trivial now that you mention it.
Wait,
Because
what's
a
trivial?
minus b, like in our case, a minus b is like between negative 2022 and like positive 2022, right?
Yeah.
Oh wait, but why does there always exist? Why can't you have like wait, surely if you have enough points in this range, then you can get a sum which adds up to zero, right?
I mean, yeah. Otherwise, the problem is false, right?
Otherwise what?
Otherwise, the problem is false.
Yes, yes, of course, yes. But yeah, I mean like, how would you prove it?
You have a bounded collection of integers which add to zero. If some of them add to zero. But what? I think you can induct, right?
Induct what?
On 2022.
How? You mean for the 2D case?
I don't know, like for this.
Like for this
specific-
particular thing, right? Yeah. Yeah, you can induct on it for this, yeah.
Yeah, well, what would the generalization of this be, though?
What do you mean the generalization?
Like the 50 dimensions, you can't take A minus B, right?
Oh yeah, no. I'm pretty sure like so once you do this, right, then surely what you do next is for the 3D case, you just collect a bunch of like 2D cases that work. And if you have enough 3D vectors, you can group them into like a bunch of 2D vectors which work. And then so now you have a lot of vectors of the form A, B. And then you repeat the same
Okay.
process with A and B, right?
Maybe.
The problem is how do you even do this one
Oh,
dimensional?
Here's how you could do it. You could like take in 3D you associate each vector with like A minus C, like A minus B, right?
Yeah.
Wait, no, this doesn't work. Okay, then I didn't say anything.
What? Wait, doesn't my idea work?
Yeah, I think so.
Like as long as they're mutually exclusive, which actually no. Can you But yeah, okay. I guess we should focus on this one dimensional thing first. Why is this so hard? This shouldn't be this hard. Okay, so you have let's say 0, and you can go up to 5 and minus 5, and you have a unlimited amount of points you can put on here. And at some point, you have to always be able to make 0 after that. Is what we need to prove, right?
Yeah.
Oh, and we also know that they all sum to 0. Surely there's some pigeonhole argument that works here, but I can't think of what it would be.
I know, like. What the hell? Okay. I'm allowed to say that word.
What?
This is a PG streamer. Come on.
Oh. Okay. Okay, so let's see. If you have, let's say, like 10 of these, then you can't have any of these, clearly. You also can't have any of these to begin with.
Yeah.
All right, let's say you balance it out with like 5 of these. Oh, right, wait, no, you can't balance out with 5 of those either.
Can't. Yeah. Wait, no, okay. So, no, you can limit each number, right?
So, wait, isn't this like, once this is 10, then like basically these all have to be 0, right? So you're just dead.
Yeah. So you have to. Wait.
So for this to work at all, this can only be like maximum. Well, like, okay, I see what you mean from the GCD thing from earlier, because like, let's say this is 0 and this is 10 instead. Then you can actually have like a single 3 or a single minus 3, right? And this would still work. And maybe you can have a single minus 5.
Where's.
But if you have both of these, oh, it just dies. Hang on a minute.
Okay, what?
So if you have unlimited 2s, you can only have one number that's negative, because you can't have an even negative number. And if you have 2 odd negative numbers, then you can add them together.
Yeah.
So the most you can have is one odd negative number. So let's say you have minus 5. Then everything else has to be 0. So like this entire thing is just dead, right? And it doesn't matter where this 10 is. Like if we say that the sum of all the numbers at the top here is like greater than 1,000, then clearly one of those numbers is like greater than 100, or greater than 10, let's say, right? So it doesn't matter what that is. Like, let's say it's 3, or like, let's say it's 5, okay. Then you just need, like, for the negative section, you can no longer have like anything that adds up to 5. But actually, yeah, you can use the lemma. Do you remember the problem, which is like, prove that if you have like n numbers, then there's a subset of them which is 0 mod n, that sum to 0 mod n.
Oh, bro, yeah.
So you can use that lemma, and then
If
you can.
have 2n minus one of them. Was it Cauchy? Oh no, Erdos, Ginsburg, Ziv.
Bruh, you remove the name. It's also not 2n minus 1, right? It's literally just n, isn't it? If you have n integers, then a subset of them.
No, that's different. Yeah, okay.
A subset of them is 0 mod n. Yeah.
Yeah.
So essentially, if you have 5 numbers in here, then
Okay, yeah.
Yeah. So the proof for 2022 would just look something like this, right? You have 0, and then you have 2022, and you have minus 2022. And then you let there be like greater than 2022 squared vectors in here. So at least one of them have to be like 2022. And let's say it's
Times
one of
2.
the... Sure. Oh, yeah. Let's say it's some random number here, and this turns out to have like 2023 vectors. Then you look at all the negative vectors, and you just cannot have more than like whatever n is here, right? You cannot have more than n. And that's a contradiction.
Yeah.
Okay, so we solved the two-dimensional version of this.
Okay, now generalize.
Um, oh yeah, and for the viewers that don't know what we were talking about when we said that lemma, when you have
Are you on the next page?
yeah, when you have n integers, there's a subset of them, a non-empty subset, which sums up to 0 mod n. This is a classic problem in like, well, I guess combinatorics really. Yeah, and the way you prove this is by considering the partial sums. So you take your n integers, I don't know, like a1, a2, dot, up to an. You take the partial sums. Oops. All the way up to Sn. And then out of these n, they've got to be something mod n. So remainder 1, remainder 2, all the way up to remainder n. Right, and this is mod n. And if any of these are 0, then you just take that partial sum. But if any of them are not 0, then they have to repeat because there are n of them, and pigeonhole principle. So you just take the two that repeat. And you subtract the two. So then we get that Sj minus Si is now congruent to 0 mod n. And so this is just equal to ai plus 1 plus dot plus a... Oh, it should actually be... Yeah, without that, I guess. Plus up to aj. So this is the subset that you can take to be 0 mod n. And so you can apply that in the previous problem here, or the problem we're currently working on.
Tony, if you got the case when they're all distinct.
No, I said that if any of them are 0 mod n, then we're just done, right?
True.
Yeah.
I must have zoned out. Okay, problem. Okay. Generalize.
Okay, so when we have a bunch of like 3D vectors, like A, B, C, then we can generate at least one vector which looks like A, B by the 2D version, right?
Oh, you just like group them into these and then...
But I'm not sure if you can put them, if you can generate like as many as you want that look like this, because you can only generate them if they're mutually exclusive.
You just take them out and then just do the same thing to the other.
Oh,
How-
no, but you can't, because once you take them out, the sum, like the total sum, is no longer.
Oh, true.
Yeah. Like, as in,
Hey. Oh, but the sum of the first two is. Wait.
oh,
Oh.
wait, the sum of the first two is all we need, right? And the sum of the first two is
Yeah.
conserved.
Yeah.
Oh, yeah, so it does work, right?
Think so. Wait, we've bounded the number of vectors you need to consider for this, right?
Sorry?
Wait, never mind. That's stupid. Yeah, okay. It does work, I think.
I think it does work. Yeah. So you can generate as many vectors which look like this as you like. And then you just keep repeating this process on these vectors to generate a vector which looks like A. And that's how you do it for 3D. And then you just keep inducting.
Yeah.
So I think we've done this problem as well, right?
Okay. The bounds is stupid, but
The bound is pretty
We'll get
stupid. But also it uses this lemma, which is like, it's not that common. I've never seen it as like introduced as a theorem. I've only seen it as like a problem.
I had a different way of doing this. But like I had a different way that I was going to do this. Attack this. Just like
Attack.
consider one.
Sorry, which problem?
Like prove this one.
The lemma, or
Yeah.
oh, you mean the like the one-dimensional case that we were talking about?
Yeah.
Oh, right. How are you going to do it?
Idea is like if you have some number, which appears like I don't know k times.
Yeah.
Then what idea again? Okay, assume k is like greater than like 20. Assume k is very large. Okay. Large. Then everything on the left side, everything over here, it must have a bounded size, right? Like say this number is m.
Yeah.
Everything here can have at most m-1 things. Otherwise, it's multiple m, and then you just cancel them out with the k's, the km's.
Right. Oh yeah. Oh
Yeah,
yeah. No, I
large.
see what you mean. That works. Yeah.
Conjugation.
But I think, do you like, don't you need to swap? Like, the number on the bottom is the number, and the number on the top is how many of them there are.
Yeah.
So don't you mean to
Yeah,
swap these two around?
The number. Wait, what? The number on the top is. Wait. Number on top is how many of them there are.
Yeah.
No, the number on the bottom is how many of them there are.
No. The number on the bottom is the number. The number on the top is
Oh,
how many
no.
of them there are. So I think you got it the wrong way around, right? Lol. Yeah, but I can see what you mean. So like, yeah, if there are loads on the top, then you just cannot get a multiple of the bottom number. And so every number on the left side, on the negative side, is also like, yeah, it's got to be less than n-1. Yeah, okay. Yeah, this works. This works too. So we don't need to use the lemma. We don't need to use the lemma on page 8. Yeah.
Oh, we can use a lemma anyway.
Yeah, we can. I mean, yeah. That's the first way I saw how to do it. It's also kind of useful lemma.
Right, and the one time you use it, it's very useful.
Yeah, exactly. If you can use a lemma once, it becomes useful.
Sure.
There's so many theorems I've never used, like butterfly theorem, Newton-Gauss line. Like, what the heck?
Yeah, who uses Newton?
Actually, I don't think
Yeah,
that's
we
true. I
can
think
try.
I actually have used Newton-Gauss line.
Oh, for that, what is it? Inner circle. Oh,
I don't think so. It was for a really old,
nice.
like, New Zealand Maths Olympiad squad selection test. I was just practicing on it. I wasn't actually doing the test. Anyway, problem 4.
Yeah, okay.
Yeah. Wow, time to do the cool fade-in effect. Whoa, look at that. Okay, it's geometry. Good stuff.
Okay, what was the problem?
I'm screenshotting it.
I'm watching the screen to see the problem. Oh wow, that was sick.
Alright, geometry. Do we do a GeoGebra diagram or do we just freehand?
We can freehand it.
Alright, let's freehand it. Let ABC be an acute angle triangle. Let me just draw a tiny diagram first.
Okay.
So I know what the diagram looks like.
It's like some medians.
Let LB and LC be the lines perpendicular to BC, which pass through B and C. Okay.
Wait, what was that? Oh, no mind.
A point T lies on the minor arc BC. The tangent to this at T at PB and PC, the line through PB perpendicular to AC.
Even that Q lies on PC. What? Oh, a nice diagram. We just scale it up.
Hang on, what's the, I haven't finished, can I, made a point. Oh, meet at a point Q, so this point is Q. Given that Q lies on BC, oh yo, it almost does lie on BC. Prove that the line AT passes through Q. Okay, AT does not pass through Q.
That's good enough.
Bro, are you kidding me? This is like one of those diagrams that's like impossible to construct.
Yeah. You just have to go with this tiny diagram.
Yeah, so clearly we're just going to solve it on this tiny diagram. Easy. Yeah.
Okay, let's draw a big diagram.
Yeah.
Okay, I've already messed up.
Bruh. I'll draw it.
Yeah, watch this.
Oh, it's a circle.
Why is it not a circle? Pressing Control and Shift, and it's not working. Oops. That's good enough.
Bruh, that's like a snapping ellipse.
Sorry. I don't know how to do circles.
Alright, I'll do a circle. You just gotta eyeball it, but it's gotta look like a circle. There we go.
Oh. Whoops. I left the Jamboard. I'm coming back.
Rip. Alright, but how did you draw those straight lines?
Just very good with my mouse.
Sorry? Oh.
Oh, I messed up.
Bro, what the heck? Are you like using a ruler on your mouse?
Yeah, of course.
Wait, what the heck? Bro, wait, how are your straight lines so good?
Oh, damn. That's not very straight. Oh, see that?
Wait, what the heck? How do you do that? Nah, these are like straighter than all of the ones that you've been drawing.
Yeah, I'm just too good. Look at that line. Look how straight that is.
Bruh.
I compete.
Rip. All right. Yeah, this is art class now.
Yeah, let's draw the perpendicular. Oh, that was clean. That was a good line.
Bruh.
That's nice. Okay, the tangent's not gonna. Okay, whatever. Try. Oh, that was pretty tangent.
That's pretty good, yeah. Yeah, so it's like tangent there. Bruh.
Oh my god, what a diagram!
Bruh. Wait, what?
Wait, no.
Bruh.
Okay, no, this diagram is worth looking at as well.
Wait, why? So why is AQT not on a straight line?
Because this angle is at 90 degrees.
Oh yeah, I guess it's slightly off. Yeah. But it's supposed to be. It's Control Z that. Right, it's supposed to be 90 degrees.
90 degrees. Oh wow, you have a cyclic quad. Crazy.
Wow, sector quad.
What should we name these points?
They're named. Wait, aren't they? Oh, right. No, wait.
No.
So, this point is PB.
Right, okay.
This point is PC. And that point is Q. And I'll draw it again, I guess. All right.
I'm gonna name it D.
No, E and
Name this
F,
one D.
surely, right? This is
E,
E.
no.
Yeah, that's E. Bruh.
Y.
Fine. Okay, D and E then. Bruh. Nice. All right, best diagram.
Look at all the cyclic quads.
Psych.
Bye.
All right, so ADQE is cyclic. What else is cyclic? Oh yeah, there are loads. If you like extend these, there are more.
Not even those. I'm just saying like this angle is 90 degrees. This angle is 90 degrees.
Yeah, but that's not a cyclic quad.
No, but
But there are lots of 90
E
degrees.
EEC PC.
E
EEC PC.
EECPC.
E B.
EBCPC.
Yeah.
Oh, right. Oh, yeah, that is a cyclic quad. BECPC. And by symmetry, CDBPB.
Okay, that's it for geometry.
Yep.
So
Cool.
now
Let's
I
go to
can-
the next problem. All right.
Tony, how have your geometry skills evolved over time?
They've gotten worse.
Yeah, so
Yeah.
this is very sad.
This is very sad indeed. Okay, so, surely we proved that, like, AQ Yeah, let's just
Okay.
prove that like a CAQ equals CAT or something.
With angles.
Yeah, just switch to angles, honestly. I never prove like collinearity except when it's like, I don't know. What's it called?
Wait, is DE EBPC cyclic?
Um, uh,
I don't think so. But
Wait a minute. Isn't this just straight up? Wait, what's it called? The power of a point, like spiral. Wait, no. Radical axis, radical center. Is Q not like the radical center of like a lot of things?
of which totally, but what
Surely,
what is it?
surely, right? Because look at this, right? So, B E C P C have diagonals
Oh yeah.
BC and EPC, and CDBPB has radical, so has
Yeah.
diagonals, and then so that means the other two diagonals form a thing, right?
Oh, true,
So
true.
EDPCPB is also cyclic.
Oh wow.
Easy.
Oh,
Um, and because yeah, okay, wait. So let's just draw in a few more lines, I guess.
and that straight line all the way. No, never mind.
I don't think we want to do that. Yeah. So okay, so angle CAQ is equal to angle DAQ, which is equal to angle DEQ or DEPC, which is equal to angle DPBPC.
Yes.
Okay. Meanwhile, angle CAT
Angle CAT is
is,
CTPC,
sorry, what? Say that
I
again?
think. CTPC by alternate second.
Oh, yeah, that's also true. I was going to say CBT, but it is also equal to CTPC.
And so this implies that CT must be parallel to PBD. Well, if the problem was true, then
Then what?
it would be done if you showed CT parallel to PBD. Right.
PBD. Why is that?
We've got that.
Bruh.
My straight lines are not going very good at the moment. We've got that like this one is equal to this, and this one is equal to this. Right.
Hang on, let me just. DPBPC is equal to that, and oh yeah. Agree. So
So similarly, TB should be parallel to EPC. Right.
yes.
Wait, doesn't that? Oh, doesn't that mean the side? Doesn't that mean that? Does it? Okay, I'm confused. No, it doesn't. Said. No, it does. Doesn't that mean that AEQD should be similar to ABTC? Wait, no, never mind. Okay. Wait, what?
That doesn't look correct.
You know, this holds infinitely if T is a antipody of A.
Does it?
Yeah.
Why?
Because PBD is perpendicular to AC.
Yes, okay, but
So then we get CT perpendicular to AC.
oh. Oh, yeah. No, you're right, yeah. Wait, so it would be, right? Wait, so as in like AT is a diameter.
Yeah.
Oh, okay.
So the problem is show that Q lies on BC, infinitely if T is diameter.
Wait, is it if and only if?
Uh,
It's not. You only
uh,
need to do one direction.
but you need to show that if T is this point, then the AQT is linear. I think.
Right. Maybe you can just do reverse reconstruction from there.
Maybe. Surely we take like moving points.
I was thinking about that too.
Like you take Q moving along BC and then Bruce tangent only at one point.
Lol.
Nah.
I mean, the nice thing about the thing that we're left to prove is that like we can rub out E and PC, right? They don't matter at all.
Wait, E and PC. What do PC do?
Oh, wait, no. Yeah, wait, no, they don't matter at all. Because if we just want to prove that CT and PBD are parallel, that doesn't involve PC or E, right?
But you're like implicitly using it in the construction of Q.
No. Q is just defined as the intersection between PBD and BC.
Okay. But in general that's not gonna work. Right.
Oh, wait, what?
In general, if you use that definition, it's not gonna be true.
Oh, yeah, okay, wait, yeah, I see what you mean.
It's annoying.
Have we even used the fact that ABTC is a cyclic quad?
Yeah. When you use alternate segment.
Yeah.
Wait, I had to we? I don't know. Not really.
I mean, we didn't even list it as one of the cyclic quads.
No.
But we used it here, actually.
Yeah. The condition is also like equivalent to CBT, similar to wait, which one is it? CBT, similar to PCPBQ.
Wait, what? BCPBQ. What?
ECT similar to PCQ.
PCPBPCQ. Wait,
What?
PBPCQ and which one?
BCT.
BCT. So that's this angle and this angle. Wouldn't that just prove that this is a cyclic quad?
What?
Yeah, it would.
Odd.
Which is supposed to be true as well, right?
Is it? Oh,
Because this is supposed to
interesting.
be... Never mind, it's not supposed to be true. Wait, what the heck?
Yeah, it is. It is supposed to be true.
Oh, yeah, of course, because this is supposed to be diameter, so here is supposed to be a right angle. Yeah.
If you surely let AT and sec BC as a point,
Like, you mean this
you
point
get
here?
yeah, you get two more cyclic quads.
Where? Oh, right. Yeah. But the diagram gets very messy.
Yeah. Oh well.
Are those cyclic quads useful?
Who knows?
Hmm.
Geometry.
Yeah. Shake my head. Geometry.
How do you solve geometry problems?
I forgot. Sad times. Okay, so I think the locus of Q, by the way, it looks something like this.
Okay. Can you prove that?
No, but you could
Nice.
prove that using like a coordinate bash. Or just
Yeah.
any other bash, really. I mean, yeah. As in,
We're
like
not doing.
the apex. It looks something like it's a quadratic, right? Because,
Yeah.
yeah, and then,
It was
um, and the apex should be on BC, exactly. And the point where it is at the apex should be where T is diametrically opposite to A.
yeah. BC. How annoying. It'd also be done, I think, if you proved AQ perpendicular to PBPC.
Right.
Or AT perpendicular to PBPC.
Yeah, but aren't those, they're like essentially equivalent, right?
I don't know if the first one is.
Oh. Oh, AQ
Maybe it is.
perpendicular to PBPC.
Wait, is that even true? Oh, it must be. So that's not even true in the general case. AQ perpendicular to PBPC. But maybe something similar is. Ugh. Not the diagram. That's it.
Nah.
That's right.
Surely, no. What if we prove that? Um, Okay, what if we prove that, like, when t is diametrically opposite to a,
Yeah.
then this is true. And when t is not diametrically opposite to a, then this is not true.
It's obvious. This is true. If and only if t is diametrically opposite to a.
What do you mean?
Huh? What do you mean? What do you mean? What do you
Oh,
mean?
right, as in, if t is diametrically opposite to a. Wait, is it obvious? Oh, because now it's just a right angle here, and this is also a right angle, so obviously it is. Yeah, I see what you mean.
Yeah.
So can we also prove that, like, if t is not diametrically opposite, then it's not parallel? That's also obvious, right?
Yeah. No, you need to prove t. If t is not diametrically opposite, then q is not on BC.
Sure, but
Probably do like using a complex mesh. Complex mesh doesn't seem too bad for this problem, right?
yeah, it doesn't. But like, surely there's a nice synth way.
I don't know. Yeah, I'm not good at complex meshes, so gotta find a synth way.
Yeah, I don't know how to complex bash either. So yeah, rip.
Find doesn't work. Wait. Wait a minute. Wait a minute. Okay. Tony, try construct AQ intersect the circle.
Okay. This point.
Yeah. So you have if you call that point like S or something. Oh, okay. I think this solves the problem.
Sorry, what?
Then I think this solves the problem.
Okay, yeah.
So you have by power of pointing, AQ times QS
Yeah.
is BQ times QC,
Yeah.
which is EQ times QPC, right?
Yeah.
So AESPC is cyclic quad.
Yeah.
So that means angle ASPC is equal to angle AEPC, which is 90 degrees.
ASPC. Oh, right. Yeah, okay.
And then similarly, ASPB is equal to 90 degrees.
Yeah. So S is equal to T.
Yeah.
Or rather, S is actually on the line. Yeah, so S is equal to T. Right?
Yeah. It's the only point
So
TPC that's on the circumference.
let S equal AQ intersect tau. Sorry, that's not tau, that's gamma. I always get them confused. And then BQ times QC equals AQ times QS equals EQ I mean, wait a minute. Yeah, this is it's not power of a point, right? It's just radical center. Like, I mean, obviously it's equivalent, but like, can't you just say that Q is the radical center of all of these circles?
Same thing.
Yeah, I guess it's the same thing. So it's equal to EQ times QPC. Therefore, AESPC, cyclic. Therefore, angle ASPC is 90. Similarly, angle ASPB is also 90 degrees. S is on gamma. P B S P C is line. S equals T. And that's just done, right?
That wasn't that hard.
Yeah, that wasn't too bad.
BMO4. I mean, BMO2 4. What happened to the difficulty this year?
Yeah, I don't know. It was like, I swear this is actually easier than problem 3.
Yeah. Well. I have to write up solutions. So. See, we did problem 4 on one page.
Nice. Didn't we use more than, like, we used 2 pages, 2 pages, 3 pages, and then 1 page?
Yeah.
It's good stuff. Alright, time to write up the solutions. Which ones do you want to take?
I can do 1 and 4.
Alright, I'll do 2 and 3.
Okay.
Cool.
Oh no.
It's time for typing ASMR. I'm pretty sure my I don't know if you can hear it because I turned my like mic sensitivity to being quite high, but like people on YouTube can hear it because I don't have a threshold for my mic for my stream.
Nice. How do you use overleaf? Where's the compile button?
You press Control S to save and compile at the same time.
Why is this not working? What? Oh, there we go. How do you have both things at the same time? Damn it, I exited.
You mean both save and compile?
Like both source and PDF. Oh no, I found it.
Oh, okay.
Where's problem one? What do you do? Problem one. There's a 7 point here. Oh, never mind.
That's because that's just yeah.
The size of the gap. Okay. What's problem one? Let me see. Oh, Dominic Yo proposed problem 4.
Oh, nice. Who proposed the other problems?
Robin Bhattacharya, Sam Beeling, Ed Kirkby, Dominic Yo.
Okay.
Okay. What packages do we have? We have Anomyton.
Sorry?
We have Anomyton package.
Yes. Enum item. Do we not? We do.
I don't see it. Wait, what?
It's line 13.
Okay, nice.
And you can even do short labels. So you can actually do I'll show you a trick. You can do this and it works.
Wow.
That's why I have the short label option.
Oh, that's crazy. War's happened.
I'll be right back.
All right. Inverse solution to problem 4. What is it? You invert a Q, I guess. What is it? You invert a Q. E and D go to PB and PC. So A goes to something on PB PC. Oh, okay. Yeah, that works.
Okay, I am back. How are you going?
Oh, nice. I finished my 2 thing. I'll draw problem 4 on GeoGebra.
Oh, nice.
And there's an inverse solution to question 4, which is actually not that hard.
Sorry?
There's an inverse solution to question 4.
The inverse of the solution to question 4?
There's an inverse solution, so you invert.
Oh, right. Interesting.
Basically, you just invert a Q with the right radius. So the gamma stays fixed.
Yeah.
E goes to PC, D goes to PB.
Right.
Then A must go to something on PB PC, which is also on gamma, so it must go to T.
Ah, okay. Interesting.
Yeah. Good stuff.
Where'd you see this?
Samuel in the chat said, you guys basically
Oh,
did the
right.
inverse solution. I did the inverse solution.
Nice.
Let's put this up. These diagrams are Geo. Solve Geo. If now that you've got that everything is like this, then stuff works. Now that you've got that AQT collinear, it shouldn't be too hard to prove that T is the entropy, right? Actually, no, if it just solves instantly. Yeah, okay. They should ask that instead of yeah. Let's see if this works. Nope, it did not work.
Are you trying to compile? Oh yeah.
Oh, what is it?
Oh, you're using asymptote. Okay.
What else do you have?
You can use ticks.
Can you?
Yeah. You just have to make all the line widths like one
Oh, I did.
width. I mean, I've never tried it with asymptote. I've always used ticks, actually. The other thing you can do though is like, you can directly export as like a postscript, I think, and you can just include the postscript as like an include graphic command,
Oh, true.
and it
Nah,
will
too much
also
effort.
be infinite resolution.
Too much effort.
Lol.
What is the thing again? I have to use package ASCII. Okay. Yeah. Um. How do you decrease size? Size and state. Let's make it. Damn, I messed up. That looks good.
Let's have a look. Oh, yo, nice. Wait, why is BC not horizontal?
I don't need it. Who cares?
Lemao. Rip. Unlucky.
You don't need BC to be horizontal. I can imagine. Rotate the page. Yeah, I finished my things.
Nice. I I'm still doing the two-dimensional case of problem 3, lol.
Oh. Okay, I can unmute my servers now. Let's read what they say about that. What do you do with triangular numbers?
I'm using your solution, right? So like,
Oh, bruh.
I'm using your, yeah, I need a triangular number because like,
Is that the bound?
yeah, that's the bound.
Okay,
Yeah,
okay.
yeah.
Right, should I pull out the guitar? Or no?
Lol, nice. You have a guitar?
Do it. Let me read this UK BMO chat. UK Olympiad chat. See what they got. Um, there's Tony Wang slander on the UK IMO UK Olympiad chat.
Sorry, say that again?
There's Tony Wang slander on the UK Discord, Olympiad
Bruh.
Discord.
What?
I
How?
don't know. Samuel, get on that.
What happened?
Huh?
What's...
They're just calling Tony Wang cringe.
They're calling me what?
No, because they're arguing over mod scale or Evan Chan Mo scale.
Bruh. Why would you use even Chen most scale?
True, true. You heard it here, folks.
Sad. Mod scale for the win. But like, doesn't even Chen's scale start at like IMO level?
Yeah,
That seems extremely skewed to me.
it seems a bit bad for
Lol.
BMO too.
Yeah. So like BMO2 problem one is like what, like -10 or
Yeah.
something.
Wait, you can use Pappas on EQC line at infinity. How does that work?
Bruh, what a troll.
What is Pappas again?
Peppers is like, um, is that one when you have two lines? It's like the conic thing. It's like Pascal's, but like the conic degenerates into two lines. Pascal's theorem, right? Where you have like the hexagon and then the 3 points are collinear.
Wait, what then? How does Papas on 4 points work?
No
Oh,
idea.
line at infinity. Wait, what? Which? It's too hard. I give up. Oh goddamn. Oh, never mind. I see. Oh, that's quick. Oh damn. Okay, you can do it. There's like a one-line Papa solution.
Bruh.
So,
Wow.
okay, apparently question 3 was a Haas problem, which is expected.
Yeah, which is what?
Expected.
Yeah, that was, yeah. I felt that as well.
Okay, let me read BMO2 discussion. Yo, how's it going?
I am almost done, I think.
Bro, Samuel.
Sorry, what?
Apparently our only viewer is Samuel.
Oh yeah, I mean, I'm not surprised.
We don't read the chat, no.
We have two. Oh no, we have one concurrent viewer. Yeah, yeah. I mean, like
That's what I left.
that's pretty expected. Like once we finish solving all the problems, people leave because like the write up is not really interesting. So you know. So
Bro, how is problem 3 the usual pigeonhole argument? Why is Q3 even a problem? Let's see what Dominic here says.
bro, how did the problem setters think that problem 3 is easier than problem 4? I don't get this. Because I just
Oh no,
realized that
apparently,
like when we were solving problem 3, we didn't even solve the part where it's like you need a lower bound, and above that lower bound it always works. We only proved that there is some number which works, right?
what? No, I think we did everything.
Oh,
Wait,
did we?
pretty sure. I mean, if we fake solve like I don't know.
I mean, I'm
Solve.
pretty sure even if you don't, like, we can. It's not very difficult to go from proving that there's one to proving that there's like some number from which above that it's like always possible.
Yeah.
Actually, wait, hang on. Isn't it trivial that above that number it's always possible? Because like if you add more decks, hang on, wait, no, no, no.
I don't think it's trivial, but it makes sense.
It does make sense, and the way it is like there are only finitely many different distributions a box can have, right?
Yeah.
And so once you pass a certain number of decks,
Yeah.
the
Of those
distribution has
systems, yeah.
some like minimum.
Yeah, yeah.
Yeah, that's a bit dodgy, but I'm pretty sure it works. You can probably formalize it.
Hey, people. Uh, no, I think it's all the pro people that think 3 is easier than problem 4.
Like people thought problem 3 was easier than problem 4.
Like Matt Eddy, Who's beyond? And
Did they get the same solution as
Aaron.
us?
I think so. Mad Eddie called it the usual pigeonhole argument.
Lol.
Tan said, "Why is question 3 even a problem?"
Why is question 3 what?
Why is question 3 even a problem?
Bruh, okay. Wait, so how do we fix this last part?
Which one? What is this? What is your like? What have you written up?
I've written up that I've proven that there exists an integer m for which, like, if there are m decks, then it works.
Is this for which, the 3D case or the 5?
The 50D case.
Wait, what? What is this? Wait, let me. Have you recompiled it?
I mean, I don't need to. You need to, right?
Let me read this. I'm pretty sure the solution should work, even if.
Okay, wait, no. The way this works is that we don't care about the number of dicks. We only care about, like, the number of piles there are.
Piles. Yeah.
And then we just prove that, like, above a certain number of dicks, you have to have at least that many piles, and then we're done.
That's obvious. Construct a histogram of the values of D. What the fuck? Oh, wait, I can't say.
Bruh.
Blur that out. In the post, we'll delete that. Tony, we only have 10 minutes left till the BMO2 ends.
Oh no.
Mods Club night when? Tony, when is the next Mods Club night?
What's what?
Club
Oh,
night.
right. Is Samuel asking?
Yeah.
Lol. Yeah, I don't know about that, man.
Okay, we'll have to come.
I think I got tinnitus the last time I went to a club. Sad.
You know, it just makes your ears stronger.
Oh, yeah. I need to train my ears. My ear training is lacking.
Yeah, true. Yeah. That's how you get perfect pitch. You go to the club. Oh.
I think I finished, but my proof might contain some typos, because I changed. I changed like the dicks to the boxes, right? We were gonna prove for like in dicks, but now we're proving for in boxes.
Yeah. Oh well. Anyway, a histogram of the values of dr. And what? Damn, this is the first BMO2 problem 4 I've solved
Wait, what? Really?
in a competition.
What do you
Like,
mean by in a competition?
Like in a mock or something.
Didn't you solve last year's?
Last year I was like, it's the Ross sequence. I can't got it.
So you like solved it by recognition?
Yeah.
Okay.
I died 2020. 2019 I misread.
Rip. Sad.
2017, whatever, 2017. That was, I was not good. 2016 and before I didn't do it. Big sad. Damn, there'd be so many BMO2s. Dominic Yeo found problem 3 difficult, so we're not alone.
Okay, that sounds good. Oh, that's the wrong way around.
What are you running up?
I'm just trying to make this thing rigorous because it's like this is very annoying to write up. Because you need to prove that like when you do this induction, everything stays finite, and because like yeah, like the 2022 changes to some other number when you go from like 2 dimensions to 3 dimensions.
Yeah.
And yeah, you just need to show that like the way it scales up does not depend on some things that it shouldn't depend on.
Yeah, fair.
Yeah.
It shouldn't though, so have fun. Okay. Let's do some groups.
Okay, I think I'm done.
Nice. We did it. Oh, right in the 3.5 hour mark.
Oh, nice.
We have we have one person watching.
Yeah, nice. So I feel like problem 1 and 2 were like pretty straightforward, and problem 3 and 4 were like more difficult. Problem 1 was
Problem
like
like, I don't know. It's like the usual approach.
I don't know, like D3 or 4, maybe 3.
I really don't know. I've forgotten how the D scale works.
Lol.
Let me look at some POTDs so I can see.
I mean, it's just like D6 is IMO1.
But well, how is D3? Like half of IMO1.
Yeah, well, yeah, I don't know. I think maybe problem 1 was like D3, problem 2 was maybe like D4, or maybe D5.
Say problem was D. Wait, this problem is.
Yeah, problem 2 was probably like D4.5-ish, either 4 or 5. 1 was probably 3 or 4. Problem 3 was like stepping like D like 8 or something, or maybe not 8, maybe 7.
D7.
Yeah. But there are so
What
many
do you say problem?
details in this problem. Like, I feel like writing it up is almost like longer than snipping solving it. Yeah, and problem 4 maybe D6, 7-ish as well.
6. Yeah. Take one. What else? What's D2? What do you say? Like D4?
Problem 2, I said D4 or
D4 and a
5.
half.
Yeah, D4.5. Yeah. So I guess that's our ratings.
Samuel, what's your rating? P2, D5. What's the D5 problem like you compare this to? Damn, there'll be no D5.
What does Samuel think problem 2 is?
He thinks this is a D5.
He thinks problem 2 is D5?
Yeah.
Isn't that what we're saying? He says no way P2 D5.
Oh. Wait, I read it as nah, no way. Problem 2 is D5.
Oh, right. Yeah. I think problem 2 is probably not D4. D4 is like pretty easy. Problem 1 is like, yeah. Okay, and then yeah, problem 3. I don't know. I still think problem 3 could be like a reasonable IMO2. So
IMO2.
maybe our solution is just bad, but like if our solution is the easiest solution to find, then I feel like it's like IMO2.
But I don't know. I don't know how D rating works.
I mean, if it's IMO2, if it's like a average IMO2, then it's D8.
It's like logarithmic, right?
Kind of, yeah.
So like, what is it? How long did it take to do problem 1? Like
Lol. I guess we'd have
And
to. It took us like
and this
18 minutes and then like 20 minutes to do problem two or
so
something.
so you square 18. I don't know.
And then your units is now minutes squared.
True, true. How much is it? How much is it? Okay, I don't think it's gonna work. Problem 4 d6. Yeah, problem 4 is d6. I agree. Wait, is there another case? Is there another solution for problem 3? It's like Samuel. I don't know. Maybe I'll type in the chat.
Anyway, it's like 30 minutes past 3 hours now, and I actually need to go do something else. So that's probably going to be it from me.
Make sure you edit the video. Ready?
Sorry, what?
You gotta edit the video.
Edit the video?
Yeah.
What? How edit video? What?
Remove bad words.
Where's the bad word?
Yeah.
What? I don't remember this.
Okay, good.
Wait, what? Was I here? Did I hear it? I don't remember this.
You must have. You must have. There's no way you didn't.
What?
Okay.
I don't remember this.
Yeah, it never happened.
Okay, cool. Oh well, that's it from us. We hope you enjoyed the stream. Honestly, if you've watched until the end, like not even like.
No one's watched till the end. This.
I mean, we have 3 concurrent viewers right now, right?
One of them is me.
Oh, right. Well, that's 2 others.
I'm pretty sure one of them's you, right?
No, I'm not watching.
Okay, okay.
But like, yeah, if you're not even like a concurrent viewer and you watch to the end, I feel like,
What's GRAM 13? I'm dying on GRAM 13.
yeah. Anyway, leave in the comments what we should live solve next. Go buy our mods merch. Don't forget to subscribe and like. We totally have
hit the
mods
bell icon.
merch. It's so good.
Hit the bell icon.
Yeah.
Support us on Patreon.
Oh yeah, and join our Discord server. It's in the channel description. You'll find the Jamboard and Overleaf also linked in the channel description. Yep. Cool. Nice. Nobody's gonna listen to this, so we can say pretty much whatever we like now.
Be sure to give us Nitro.
Yes. Don't forget to join our server and give us Nitro. That would be very helpful.
Please send money.
Yeah. And
PayPal is in the description.
Yeah. Mm-hmm. Cool. Well, yeah. See you all next time.
Thanks,